So just before we left, we introduced this very first vector associated with the intrinsic system, the tangential unit vector, and this is what we had in terms of the velocity as well. So the tangential unit vector is p prime and the velocity vector is s dot times et hat. And we said that it's more to do with the path rather than the body. So now we need two more unit vectors, et hat other than et hat, which is en hat and eb hat, which I already did on the whiteboard, but we'll kind of summarize that on the slides now. So second vector is the principal normal, that's what it's called. It's denoted by en hat that you see in a green font over here. And when you have a surface or rather a path which is curving, it will always be towards the center. So that's something just like your centripetal acceleration. This unit vector is always towards the center. In other words, it's towards the concave side. So for example, on the path when it's coming here, it will be in this particular direction and it will slowly change that and go to the other direction. So where there's something straight, then essentially that's where the changeover takes place when it changes over from a concave to a convex kind of a contour. The principal normal is undefined if the aircraft is moving in a straight line, and this is understandable because remember that instead of a curved path, if you had a straight path, then there's no specific reason for your en hat to be in this direction or this direction or this direction, any direction. All of them are equally good candidates for the normal. So in other words, there's no distinction as such between the normal and the binormal as far as the rectilinear coordinate system is concerned. Any plane which is perpendicular to the tangential unit vector, you can take one as the en hat, and then automatically the one which is perpendicular to that on the same plane will become your eb hat. It's only when there is a curvature that a non-zero curvature, that is, then you would have a specific direction for en hat, because you have what is known as the osculating circle, and therefore that circle is on an osculating plane. So that plane identifies where en hat will be. We know it should be perpendicular to et hat, but there's an entire plane on which you could have unit vectors perpendicular to et hat. Which exact direction is chosen for en hat depends on the oscillating circle and the oscillating plane, and that's how your en hat is identified when there is a non-zero curvature, right? So for a curved path, which is what our interest is right now, the principal normal unit vector is directed, as I said, always towards the change in direction. So this is, see, it's going this way. Now it wants to change the direction towards that. So now, though we have not introduced kinetics, we know that force is the cause of any change that happens, right? So for example, if it's a straight line path on which a particular particle is moving, let's say this is particle P of a certain mass m. Now it's moving at, let's say, a constant speed u, okay? Now if that u has to change, then there has to be a force, right? So this, if the force is, let me use a different color. Now if this force is in this particular direction, then that force will make u to increase, right? On the other hand, if the force is in the opposite direction, obviously it will make the speed to decrease, okay? So this is essentially your Newton's first law, which says that unless until acted upon by a force like this, whatever motion is there, it will continue. Whether it's constant motion, it will continue with the same speed. That's essentially what we are talking about over here, right? Now that's good enough in a rectilinear motion. These are the only two directions in which the force can be. But suppose the particle is not restricted to be on that line, but it just happens to be on that line, just like in the case of an aircraft when it is in cruise. So an aircraft is cruising. It's not that the aircraft is incapable of changing its altitude or having a sideward motion by essentially deflecting its rudder and ailerons. It can do all of that, but just that is the phase of flight in which it is going. But now if you want to, in that same path, if you want to change, then obviously these are the only two options for f. Of course, you can increase or decrease the magnitude of f, but in terms of the direction of f, these are the only two directions. And one of them increases the speed, the other decreases the speed, right? Now you come to an option which is very different from these. Let me use a third color. So suppose you have a force which is perpendicular to the path. What happens then? Any takers? Yes. So whereas these forces which are tangential, so in other words, the forces components are all along your ET alone, so then it only changes the magnitude of the speed, right? So in either case, force will cause an acceleration, okay? Force is, which is essentially a net resultant force being non-zero, will cause an acceleration. But acceleration, remember, is the rate of change of velocity, and velocity is a vector. So vector can change either by changing its magnitude, which is what this is, which is the velocity of p in I. Its magnitude is what we have defined here as u, right? So that can increase or decrease when your f is along the ET hat. But now when it is along En hat, or for that matter EB hat, if it is along En hat, what it does is, you originally had your curvature kappa equal to 0. You had your torsion tau equal to 0 throughout, and therefore I put a 3 lines over there to say that it's not 0 at a particular location but throughout the path, right? But now if that is no longer valid beyond this point, when I bring in this any one of these forces for that matter, these forces, what they will do is only change u, so your kappa and tau remain 0. On the other hand, if it is f is like this, and you have defined your normal, which is perpendicular and to the tangent to the path, but it's on the plane of this whiteboard, then essentially what it does is it changes your kappa, it changes your curvature. So in other words, that force essentially will be something which will take you on the curved path over there, right? So it's essentially going to go on that path. So that's the, if you want a change in direction, you should have a force component which is perpendicular to the path. If you have it tangential to the path, it can only change the magnitude, it cannot change the direction. And if it is exactly perpendicular, then it changes only the direction, doesn't change the magnitude of the speed, okay? So a vector has two aspects to it, the magnitude and the direction. If you want to change the magnitude, you have to have a tangential component of the force. If you want to change the direction, you have to have a perpendicular component of the force. It could be along the normal, then kappa changes. If it is along the binormal, which is perpendicular, so I can have another force which is coming into the board or out of the board, that will change your tau, essentially taking it out. But in the trivial case where you just have a straight line, there's not much of a distinction between what each of these is, because as I said, you cannot distinguish between the normal and the binormal. The distinction between normal and binormal happens only when you have a curved path, at least a planar curve, if not a spatial curve. So this is what we are trying to, and of course the most general case would be you have a part of this and a part of that, so some essentially a resultant force, something like this or something like this, which is at an angle to the path, a non-zero angle, a non-90 degree angle, then it can change both the magnitude as well as the direction of the particle's motion, the speed. Okay, so for curved path, the principal normal unit vector is directed towards the change in the direction of the unit tangent, which is what we showed over there. So the change in the tangent, see, you can see the tangent very clearly is this direction. If we look at a point a little further away, the tangent is going to be this way. So in other words, the rotation is towards this way, which is essentially your anti-clockwise kind of a rotation, which means that your normal is in that particular direction. That's the meaning of this particular statement over here, right? And that En hat, as we showed on the whiteboard in the morning, is nothing but Et hat as far as the direction is concerned, but that's not having a magnitude of 1. And since we want unit vector, which is why we are putting a hat there, therefore we have to divide by its magnitude to ensure that this is a unit vector. Okay, but it's already ensured that it is perpendicular by the prime that you have over there. The only thing, because any unit vector, remember, if it has to change, its magnitude cannot change, it remains a unit vector. Only thing it changes the direction, and that direction will always be perpendicular to its existing direction, and that is why Et hat is always perpendicular to En hat as soon as you define it with a prime over here, right? But to ensure that it's also a unit vector, you have to divide by its magnitude. Now we can put the same thing in terms of the position vector P, and because remember Et is defined as P prime, therefore once you substitute, this becomes P double prime on the top and the magnitude of the same vector at the bottom. Okay, so now you have just like you could define Et in terms of the position vector, now you have a definition for En also purely in terms of the position vector. Now the derivative of constant magnitude vector, as I already just mentioned, is always perpendicular to the vector, which is why as I said, these two are perpendicular to each other. In other words, their dot product will be 0. Coming to the next statement here, above vector, that is essentially you're talking about the principal normal, is directed towards the center of the curved path. So it's always towards the concave side, as I already mentioned, whereas in this portion it will be towards this direction. So it's always towards the center there of the curved path, something like the centripetal accelerations. So based on the local curvature at that particular point of the path. Okay, now that we are done with the tangential unit vector and the normal unit vector, the third one, the binormal unit vector, has to be introduced. Simultaneously, we can introduce the concept of the curvature as well, that is your kappa that we talked about here, right? So once again, to remind ourselves, on the path, you have to have these things. One is the particular point on the path. At that point, you're looking at a slope, you're looking at a curvature. All of these have great relevance in the understanding of dynamics and how they change with time as well, right? So, and to get to the slope, obviously you need a first derivative. To get to the curvature, you need the second derivative, as you already know. Now, therefore, the second derivative in this case is what we call as kappa, the curvature, and that's equal to 1 by the radius of curvature, and that is nothing but the second derivative of your position vector in terms of the magnitude, because this kappa is a scalar measure number of the curvature vector, and rho is the radius of curvature, also a scalar quantity, right? And remembering that P prime is nothing but your Et, therefore this is just Et hat prime's magnitude, which is what we have defined as kappa, which is a concept that Ferret and Frenet and Serre had introduced, which we talked about earlier, right? Now, so that's En hat is rho times E hat Et, because this curvature comes through that. So you're essentially substituting for what we had as the magnitude of these two quantities in the previous slide. We are just putting that as 1 by rho, and therefore we can write now En hat in terms of Et. If you know already Et by taking the first derivative of the position vector, then you have to take the derivative again and multiply by the radius of curvature in order to get your En hat, because Et hat prime is having the unit of 1 by distance. That's the dimensionality. It has 1 per meter. Now that you have the curvature which is multiplying that, it essentially takes care of that, because radius of curvature that you have, therefore that is in length, and this is 1 by length, and therefore once again you have a non-dimensional quantity over there. Okay, then you have Et prime. So is essentially putting this in a different way, in case you knew En, how to get to Et prime. So that's another possibility over there as well. Then now 2 unit vectors are not enough. In all those cases we had I, J, K. We had in the polar or cylindrical coordinate we had ER, E theta and K hat. Similarly here and in spherical we had ER hat, E theta hat and E phi hat. Now here also we already introduced ET hat and EN hat. The third one is usually in all systems, because we are looking at dextral triads, are always the easiest to introduce, because now that you have two of them, the third one has to be perpendicular to both, which means a cross product is easy way to express that. And once you do that, you will have your EB hat, because once you know ET hat and EN hat, two vectors, there are two possibilities for your EB hat. It can be either coming out of the board or into the board. Okay. Now, which is actual is because we introduced the tangent first, similar to your I hat. Then you introduced your normal, which is similar to your J hat. You want K hat to be following that dextral triad rule, so that ET cross EN is a positive EB. Okay. Whereas EN cross ET will be a negative EB hat. So now that we have all these three unit vectors, we can move from the velocity to the acceleration. Just before we broke for lunch, remember that we had introduced the velocity vector of P to be the simplest that we have known so far, considering Cartesian, cylindrical and spherical. Amongst all of them, we saw that the expression for the velocity, which is within the bracket here, s dot times ET hat, is all that you have as far as velocity is concerned. So powerful this particular system of coordinates, the intrinsic or natural coordinates, is that this is all that you have. Now we want to go one step further, to go beyond velocity to acceleration. We have to take the time derivative, and that has to be done with respect to the inertial frame of reference. Strictly speaking, there should be a I pre-superscript in both these expressions on the right hand side. And once you have, yes, Lalita. Okay, good question. So remember that I had talked about an osculating circle. Okay, so you're essentially saying there is a path. Okay, so at some location we want to get, this is the location P, okay, where we want to get the curvature, let us say. So we take one point just before that, which we'll call as Q, and one point which is just after that, which we call as R, right? And we know that when we have 3 points, 3 adjacent points, so this is, you can think of this as minus ds and plus ds, okay, where we are going to eventually take the limit as ds tends to 0. So that's essentially coming back to the point. Okay. Now when we have 3 points, we know that there is a unique circle that can be drawn through 3 points. Okay. So suppose we draw that circle. Now that circle is valid only for that particular point P. If I drew at some other location along the path, I would get a different circle. Okay. Now this particular circle that you have, its radius is what is your rho. Okay. And kappa is defined as 1 by rho, or rho is defined as 1 by kappa. Okay. So that's how I get kappa. And because it's a function of the location, both of these quantities are functions of s, where s is the arc length, which in turn is a function of time. Yeah. So this is what in the morning we introduced as the osculating circle in the osculating plane, and which is what makes your see, already we had an ET hat. This is what makes your EN hat unique, because it's on that plane, it's on the oscillating plane. Okay. If we didn't have that EN could have been any vector which is having a magnitude 1, which is perpendicular to the path, which could be an infinite number of vectors in the plane which is perpendicular to ET hat. But we have one specific choice because we have the oscillating circle in the oscillating plane, and this EN hat is defined to be on that plane. Any other questions on what we have done so far? We have introduced the tangential, we have introduced the normal and the binormal, and of course the curvature and the torsion. Shall we move on? Yeah, so now that we have the velocity in the simplest form that we have known as yet, s dot et hat, we can get to the acceleration by taking its time derivative with respect to the inertial frame of reference I. When we do that, we have a quantity inside which is the velocity, which is a product of two quantities. So you invoke the product rule. So we take the derivative of one of them, keep the other the same. Then again, we do vice versa and add those two, which is what you see over here. Very simple and straightforward. Just like velocity, we had the simplest ever expression amongst all the coordinate systems that we have looked at and those we haven't looked at as well. Similarly, for the acceleration also, you just have a two-term expression, and this is the most general case of motion of a particle in a three-dimensional, arbitrary three-dimensional spatial curve, right? So it has just two terms. One is having a measure number along the tangential direction, the other is along normal. So the beauty of this particular system is that the velocity does not have a normal component, does not have a binormal component, and the acceleration does not have a binormal component. It has only tangential and normal components. Okay, so makes things much more easier to analyze with this at this level. Okay, so which is why this this particular system, coordinate system, is so powerful. So you have, and what is the magnitude along et hat, the tangential direction? Very intuitive. It's just the arc length is going, so you want to see how the arc length is increasing with time. That is the magnitude of your speed, magnitude of your velocity, which is speed. Now the second derivative of that essentially gives you the tangential acceleration. So this is the tangential acceleration s double dot. Similarly, you have a normal acceleration, and that is present only when you don't have a curved path. Because if you have a straight or rectilinear path like here, then what happens is your kappa is 0 and rho is infinity. If rho is infinity, this term vanishes, and this is all that you have for your straight path, straight motion, which we are very familiar with. In fact, at that point in time, we just call it as x double dot I hat. So just that I hat happens to be et hat in a more generic sense, and your x double dot happens to be s double dot in a curved path. Now, this particular term, you see that it has an s dot squared. So essentially, it doesn't have a second derivative with respect to time. So it's very similar to all of that we considered, namely Coriolis or centripetal accelerations. All of them had either theta dot squared or r dot times theta dot. So something very similar to that, you're getting an s dot squared, a non-linear term that you are having. This is linear, this is also linear. The first time you're encountering in this coordinate system, the non-linear term is this, which is s dot squared. And of course, you have a rho in the denominator as well. This is also an unknown, remember, because the path is still unknown. It's just an arbitrary curve that we are talking about. So rho of s is also an unknown curvature that you have, which is essentially 1 by your kappa, right? So this is going to be again very useful for some of the problems that you're going to solve in your next homework. So I hope everything is quite clear as far as this is concerned. Okay. So acceleration, as I said, is only in the tangential and normal directions. The expression is quite simple, and you have s dot, which is the speed, and s double dot, which is a rate of change of speed, which is the change in the magnitude of the velocity, which is what is contributing to the tangential component. But everything put together, those new things that we discovered, like Coriolis and centripetal, are all lumped into this single term. Okay, yeah.
You said it is three-dimensional. Where is the torsion in this?
Ah, very good question. So here, see, torsion doesn't affect expressions up to the acceleration. If we go to jerk, which Daniel pointed out last time, which is the next level, then you will get the torsion coming into picture. Which is why you would see, strangely, I introduced curvature along with the binormal, not along with the normal. Okay. With the normal, you don't have the need for curvature. Only when you go to binormal, you need the curvature. Now you already have 3 unit vectors. Where will the torsion come? When you want to go for jerk and beyond. Yeah. Okay. So how is it useful? Especially when you're looking at aircraft dynamics, looking at complicated maneuvers. This is not as complicated as many others can be, but essentially your split test maneuver, where you're looking at a 90-degree roll followed by an additional 90-degree roll, which is a 180-degree roll totally, and then you're essentially making this loop, which is like a semicircle approximately, and then you're going to fly at this particular altitude, and because of the roll that you have already had, now it's upright. Okay, so for a short time it became upside down that you see in this particular situation, right? Now, this is a situation where you want to sacrifice the altitude in order to get to a higher speed, okay? And this is typically employed, especially when you want to get out of a dogfight. So you're having a dogfight with an enemy aircraft, and suddenly you want to escape that. This is one way of doing that. The other way is you can go upwards. So essentially you're sacrificing speed for altitude. Okay, it depends on how the pilot and this particular aircraft is surrounded by your enemy aircraft, because it might not just be a dogfight with a single aircraft. You could have enemy aircraft at the back as well. You, depending upon its altitude, you might either choose to do this or to do that. In one case you're sacrificing speed, the other case you're sacrificing altitude. What we are shown in this picture is where you're sacrificing the altitude, you increase the speed and you escape from that location, assuming that the other aircraft, the inimical aircraft, are above that or at the same altitude, and therefore you're flying now at a lower altitude to escape. Now when you have situations like this, so far we have not yet introduced rigid body, so all these rotations like roll that you have, and then the pitch, that pitch change that you have, all those things we are not yet able to handle. But in terms of the path alone, you see that it's a curved path that you have. It's a planar curve. You don't have torsion. You will have curvature for a part of it. Here the curvature is also 0. Here also the curvature is 0. Just in the semicircular path, you will have a non-zero kappa to deal with. But essentially, in handling such paths, you will see that if you use the ET, EN, EB system that we just introduced, it will be very useful. In fact, EB will not come much into the picture because it's always throughout this, it's perpendicular to the screen that you have over here, because it's a planar curve that we are looking at. Okay, but in reality what will happen when you have a roll motion is that there is a possibility of the dynamics beyond just pitch, altitude and forward coming into picture, and there could be some couplings that are happening, but we will not get into those complications right now. But just rest assured that now that we have EB as well, and a possibility of tau also not going to 0, being non-zero, which means that we can handle even that situation where, because of both these dynamics, one is the dynamics of forward, altitude and pitch, the other is of roll, yaw and sideward motion. Even if all of them are present simultaneously, you would still be able to handle, because we have the capability of handling from the tool set, kinematic tool set, we have the intrinsic or natural coordinate system with which we can do that. In fact, I think some of the homework examples will help you understand this a little better. Let's get on to a few other things. Yeah, I think this concept we already introduced, but we will look at it from a slightly different perspective. We remember we already introduced kappa and its reciprocal as rho. So for general 3D parameterized curves, there's another way of looking at it, and this is a purely geometric thing, may or may not be directly helpful for you many a times, but when other things that we already showcased, the simple things that we showcased, are not sufficient, you can typically utilize this, and this can be proved, but it's purely mathematical and geometric. I do not want to get into that. Okay, so it's p prime crossed with p double prime divided by p prime whole cube. All of them we are talking of magnitudes only, because we are talking of a scalar quantity, namely a particular measure number of the curvature and the radius of curvature, which is the reciprocal of that. Okay, so where the derivative with respect to the parameters, so this prime remember that wherever it's the default, we have said that it is the derivative with respect to s, but in this particular expression it could be anything. You could take the derivative with respect to time, you could take but all of them have to be with respect to time then. If it is with respect to the arc length, then all of them have to be with respect to the arc length and so on, or any other coordinate for that matter, some theta or whatever, which defines your position vector. Essentially, you're taking the first derivative, the second derivative with respect to them, and calculating this ratio of magnitudes. Then you will see that you will end up with the curvature. So sometimes P might be known as a function of arc length, sometimes it might be known as a function of time, sometimes it might be known in terms of some other parameterization that you have, let's say theta, or it could be any of the Cartesian coordinates also, x, y, z, depending on the problem. And when you have that, you can take advantage of this. You don't need to convert P as a function of S and only then be able to calculate it, because if you already know P not as a function of S but as a function of one of these other things, either a parameter or time, then you might as well take derivative with respect to that. So that's the generalization of that prime's meaning in that particular expression. But for the rest of the course, whenever we say prime, we will mean d by ds. Just here alone, prime is much more generic, any derivative, okay, but consistent. Now this, whatever we said for 3D curves, obviously as a special case works for the 2D curves as well. The curves are parameterized by the arc length. As an example, we take, suppose P is a function of S instead of time or theta, then very easily you can see that the magnitude of P prime, which is nothing but the magnitude of your tangential unit vector, because it's a unit vector, is 1. Okay. Similarly, the second derivative is perpendicular to the first derivative, because that's how, remember, you got the normal En hat. Okay, so this is like saying En hat is perpendicular to Et hat, which is quite obvious, right? So now once you have that and you make these substitutions into this, you will see that you get kappa is equal to the magnitude of your P double prime that you have, and which is quite evident, because just like I think in one of the previous slides I mentioned that here, oops, okay, or maybe we are not, yeah. So we had mentioned that the slope is the first derivative, the curvature is the second derivative, and that's essentially what we are looking at over here as well, that it's the second derivative that we are dealing with, which is the curvature that we are talking about, right? Now, so it's just taking special cases of this, because this is a general expression. For one case, we have taken that prime is derivative with respect to S. Second time, we want to take the derivative, let's say, with respect to two Cartesian coordinates y and z. Then if you use the same equation with now x prime, because prime is now d by dx, therefore x prime will be dx by dx, which is 1, and x double prime, because it's a constant now, is 0. So once we substitute that into, and similarly for your y prime, y double prime, z prime, and z double prime, where now we are not changing that prime to mean with respect to y or z, but continues to be with respect to x. So this is dy by dx, this is dz by dx, and then the second derivatives again with respect to x. Okay. So once we have all of that, once again you will see that the curvature gets to our typical meaning in terms of how these things are dealt with in the Cartesian coordinate system. Okay. So that's as far how much we need to really know as far as the intrinsic or natural coordinate system is concerned, and a lot of that will help us also in understanding a new concept that we would like to introduce, and this is again very useful for some of your homework as well, which is why even though in your textbook, so-called textbook, it's chapter 3, so far whatever we have completed is chapter 1. Okay, so now instead of going to chapter 2, we will go to chapter 3, because the chapter 2 covers the rigid body kinematics in your textbook. We want to finish off everything with respect to the particle and then come back, or rather it's the other way around, I'm sorry. Here angular velocity is something that is not associated with a particle but with a rigid body. Okay, so we want to complete all of kinematics before we want to get to kinetics, whereas in your book they get into the kinetics of the particle, so that they finish off with the particle dynamics fully. Particle kinetics followed by particle kinematics followed by particle kinetics is how they do it, first and second chapters. So we will skip the particle kinetics, we'll do all of kinetics together later on, So we will get directly into the rigid body kinematics, wherein the only difference is, because now we know the center of mass can be treated as a particle, so all of the particle kinematics we have studied so far is valid for the translational motion of the rigid body. Only the rotational motion of the rigid body now has to be introduced anew, which means that the concept of angular velocity comes into picture. Now, if you're looking at what is known as a simple rotation, which means that there is a particular vector about which the rotation takes place all the time. So essentially you're talking about the angular velocity almost like a angular speed, and therefore like a scalar quantity which you typically use when you're dealing with it in high school kind of dynamics problems. But now we will try to enlarge the scope of that, make the angular velocity a three-dimensional entity, and it could have any arbitrary direction, but we will en route visit the concept of the simple rotation as well. Okay, so for that, because to introduce angular velocity is a fairly easy concept, so you don't the learning curve is not very steep, so it's something that we can understand. But in order to do that, we'll go back to our fourth class where we looked at some of these aspects, and these aspects will be utilized today in defining the angular velocity. So very quickly we'll go through that. Any derivative, as you know, in differential calculus is introduced by the concept of the limit of a change taking place, and essentially that change you're taking the limit as it goes to zero, and therefore looking at something else changing in the same duration in this case, which is the derivative with respect to time. When you want to do that, you have an expression for the vector functions which is similar to that for the scalar functions. So remember that this is the exact same derivative definition we used for scalar derivatives. It's valid for the vector derivative, just that here we have to ensure that we put the superscript I, and therefore this limit is also taken in that particular frame of reference, because depending on the observer's frame of reference, the value for this limit will change, because in that same duration delta t, for one observer fixed to a particular frame, the change in v will be different from for some other observer on a different frame of reference, which is why during the same duration delta t you could have a different change, and that's why the frame of reference becomes very critical over here. Now the derivatives of vectors, as far as this particular course is concerned, we will do and deal with only derivative of a vector with respect to a scalar. So t is a scalar or s is a scalar. So we will take derivatives only with respect to scalars. But maybe you are already aware that you can have derivatives of vectors with vectors when you have what are known as gradients, or you have the curl, or you have the divergence, etc. So you can have those as well, but there's no need for that in rigid body dynamics. So from our course point of view, the derivative will always be with respect to a scalar variable, but we need to ensure which frame with respect to which the derivative is taken. And therefore, in our case, the derivative of a vector will remain a vector, because you're taking derivatives with respect to scalar, whereas when you're taking with respect to a vector, you can end up with higher order tensors like a dyadic or whatever, which is how, for example, the deformation gradient tensor is defined. You will see in your deformable bodies course or the structural analysis course, you will see the introduction of that particular concept, where you're taking the derivative of a vector, which is essentially the displacement vector, with respect to the position vector, which is also a vector. So when you have a vector to vector differentiation, you end up with a second order tensor, which is what you will define as a deformation gradient tensor, from which eventually strains will be defined. Now some of the things again which we earlier listed for scalars is valid for vectors also. So if you have a sum, one vector is a sum of two vectors, then you can take the derivative of each of them separately and then sum it, rather than have to sum it and then take the derivative. So in other words, the summing process and the derivative process can be interchanged. Similarly, when you have a product, you know that you can have it as u dv plus v du, and that product is in three different types. One is a product of a vector with a scalar, one is a product of a vector with a vector, but two different ways of doing it. One is a dot product resulting in a scalar, the other is a cross product resulting in a vector. And in all cases, that uv differentiation d of uv becomes u dv plus v du. That is what we are using, and retaining that type of multiplication. Here the multiplication is just of a scalar with a vector. It remains because that's what you had in the definition of the original function. Here you had a dot product, so it remains a dot product. Here you had a cross product, so it remains a cross product. Only thing that is changing is that type of product, but essentially it is UDV plus VDU that you are using over here. So it's just a revision, so I'm going through it a little fast. So once again, I probably wouldn't tire saying this, that you need these three aspects for starting any problem: a frame of reference, at least one, and especially now that we are slowly venturing into rigid body dynamics, you'll have at least two. One is the inertial frame of reference, the other is the body. Name could be an aircraft. So I could have a reference frame I, another reference frame A, okay? And you'll have corresponding to each of them a coordinate system, corresponding to each of them a set of unit vectors as well, right? So if you have an arbitrary vector v, then we saw that it can be expressed in terms of the Cartesian coordinate system this way, and its time derivative in general will involve the derivatives of I, j, k as well. So which is why you see the I dot, the j dot, and the k dot terms as well, because this I, j, k could be a body fixed frame, it could be an aircraft fixed frame. So on the aircraft, your I, j, k compared to the I, j, k of the ground fixed frame can be changing because of pitching, yawing, and rolling, right? So when you have that, you should take care of your I dot, j dot, and k dot as well. So are these unit vectors changing? Obviously they do in a general case, but you could have special cases or simpler problems where they do not, right? So both are possible. That's why, since they could in general change, that's why you need these frames of reference. All those things become so critical now that we are venturing slowly from particle dynamics to rigid body dynamics. But because we learned this good habit as part of the particle kinematics, translating that to there, it seemed like an overkill, too simple a problem to bring in all those concepts. But now that we are aware of those concepts in a simple problem, in a slightly less simple problem, we can see the utility of those. So that's why those are important. And then of course we just talked about frame of reference, but inertial frame of reference also will become important as we go into kinetics. As far as kinematics is concerned, there's really no need for inertial frames of reference. Why inertial frames of reference are needed? Because to apply the kinetic equations, especially F is equal to ma, your second law, you need an inertial frame of reference, otherwise it's not valid. That's why we introduced it a priori, even though it was not directly necessary at that point in time. So with Cartesian coordinates, of course, it becomes even easier to differentiate. So in other words, a frame of reference can be inertial or non-inertial. Similarly, a coordinate system can be Cartesian or non-Cartesian, okay? And you end up with four combinations. The simplest case being inertial frame of reference with a Cartesian coordinate system. You could have also an inertial frame of reference with a non-Cartesian coordinate system, which is what we saw in terms of the polar coordinates or cylindrical coordinates, spherical coordinates, intrinsic coordinates, etc. On the other hand, you could have a frame of reference which is non-inertial and either Cartesian or non-Cartesian. So all four possibilities are there, but once you have the most general case of non-inertial frames of reference and non-Cartesian coordinate systems, then sometimes those kinds of systems are specifically made for a particular kind of a problem, and therefore make the problem solving a little simpler overall, even though the differentiations involved will be quite difficult because you're having, let's say, the r theta system or r theta phi system, or like what we had in the intrinsic system. Then the differentiation is slightly difficult, but framing the problem becomes very simple, because you saw how simple the velocity was, just one term, how simple the acceleration was, just two terms, which contained all of those complications of Coriolis, centripetal, etc., apart from the regular terms like what you have here, like your dots and the double dots of the magnitudes as well. Okay. Now the frames of reference can be regarded when you're essentially dealing only with kinematics and not getting into kinetics. Mass doesn't play much of an important role, neither does inertia, but because this concept is going to be utilized when we get into kinetics as well. In fact, becomes more relevant and useful over there. So then you can think of the frame of reference in general, like for example the I frame that we have been introducing. It's much easier for you to think of the aircraft fixed frame A, because you can think of it from going from the center of mass through the nose. I call it the x-axis. Similarly, the y-axis and z-axis, I can define it in a particular way, right? So it's always fixed to the aircraft, and you can see the aircraft, and therefore you can think of or imagine what that frame of reference means. But it's not necessary for the frame of reference to be associated with a body. It can be just a intuitive thing, just an imaginative thing that you're thinking about, a fictitious thing. So therefore, you can always think of it as a massless rigid body, okay? Even if the rigid body has a mass, of course, you can associate a frame of reference with it. But if you're thinking of a frame of reference in the absence of a rigid body, it's essentially a floating frame of reference, then you can think of it like a massless rigid body, because that's what it essentially is. So the corollary, of course, is that any rigid body that you have, in our case the aircraft for example, or it could be a rotor blade which you're dealing without its flexibility, then you can deal with it as a rigid body, and that rigid body can be serving as a frame of reference. Okay, the frame A that we talked about is a classic example of that. Now, to the frame of reference, we will assign or define one or more coordinate systems. So far we have been introducing only one frame at a time, one frame of reference at a time. So, and we had a choice of these coordinate systems, Cartesian, the cylindrical, spherical, and or natural. But once we have more than one frame of reference, it's not necessary to have the same coordinate system with each one of them. You could have with one of them a Cartesian coordinate system, with the other you could have a natural coordinate system. For example, with respect to the A fixed frame, aircraft fixed frame of reference, you could have the natural coordinate system. With respect to the inertial, you could continue to have a Cartesian. That might be helpful in a particular problem. So problem by problem, case by case, we make the decision in terms of introducing a certain number of frames, and for each frame, which is the appropriate coordinate system to choose, so that our workload becomes lesser. In other words, we are more efficient at arriving at the solution. We do not want to do donkey's work to end up with the same solution, when we could do it much simpler way, which is essentially what the choice amounts to. Because as I said, there's no right or wrong choice. It's just whether you want to do drudgery or you want to do it in an efficient manner. That's how the choice is done. Okay. Now, again, starting with things fairly simple. Now let's say take two frames. One is the blue colored frame, the other is the yellow colored frame that you have over here. The blue colored one, I'm calling it as the A frame, and the one which is yellow, I'm calling it B. Not very intuitive. And then you're talking about the A frame. You're essentially having unit vectors associated with it. So this is typically how we would, so that we don't need to explain many a times. So whatever letter we use for a particular frame, we will use the uppercase to define the frame, and the lowercase of that along with 1, 2, 3 subscripts in order to get you to your unit vectors. So to the frame A, which is uppercase A with a circle around it, we introduce A1, A2, A3, and A1 and A2 are in the plane of this screen. A3 is perpendicular, as you see. This circular arrow essentially means a right hand thumb rule, and which means that A3 is coming out. So similarly, you have a B1, B2, and again B3 coming out. So in other words, for this simple problem that we're looking at, A3 and B3 are coincident with each other. Remember, all these are hat-ted quantities, so they're all unit vectors. Magnitude is the same, only they differ by direction. But A3 and B3 do not differ even by direction, so they are identical, A3 hat and B3 hat. Okay. Now, how they are different from each other is just by an angle theta, which is the rotation about the third axis, and that angle theta that we have shown here, because of which B1 hat is different from A1 hat in terms of direction. Magnitude remains one, but similarly, your A2 hat and B2 hat are differing from each other only because of that theta, and that only changes again the direction, keeping the magnitude the same, right? So we consider two frames of reference, A and B, with the corresponding coordinate systems. In this case, we have considered a simple Cartesian coordinate system, which of course involves a dextral set of orthogonal mutually perpendicular unit vectors, which are fixed in each of these frames of reference, namely A and B, and those are listed out here, right? Now, if you look at this particular vector V that you're looking at over here, this vector V, which is in white, now that has, like any vector, it has a certain magnitude, which means the length proportional to the length of this arrow that we have drawn, and of course a particular direction, right? Okay, the way this particular vector V is drawn, it's along the B1 hat direction. Okay, so now the same thing can be expressed in the B system very simply, because its components along or measure numbers along B2 and B3 are 0, right? Whereas the measure number along B1 is its actual magnitude V0, which is what we are putting over here. Okay, but it's not compulsory for us to express it only in the B system. We can express it in any other set of unit vectors, and which is what we do over here with respect to the A system. Once again, the third measure number remains 0, but the second measure number changes from 0 to a non-zero value, because you have a non-zero theta. If theta equal to 0, you can see that this again goes to 0, this cos theta becomes 1, and therefore you just end up with V0 B1 hat. It's only because theta is non-zero that this A system and B system are different from each other, because of which now we have introduced not only an A1 hat term but also a A2 hat term with the cosine and sine theta multiplying the magnitude of the vector V, right? So the same vector that we had in different frames of reference and our coordinate system doesn't change the vector itself. So in other words, the vector is entirely defined by its magnitude and direction. It doesn't matter, nothing else matters to it. But the choice of the frame of reference only gives us a way to put it in numerical form or an analytical form to get to the measure numbers, and there it's entirely up to the analyst's choice in terms of what they would like to do with it. Okay. This is an obvious thing. When you're differentiating with respect to time, since it's a vector and it has a direction, therefore it's a function of time. The answer depends on, first of all, its magnitude, because even if the direction is not changing, the magnitude could be changing, because of which it could be a function of time. The other thing is the direction changes, or both will change, right? So as far as the second thing is concerned, whether the direction changes or not is not dependent only on the vector. It depends on the observer also. So there's a subjectivity involved. It's not objective. Why is it subjective? Which is why we have to specify which frame of reference we are taking the derivative with respect to, because the observer is fixed to that frame. More often than not, we are observing it from Earth, and therefore we are looking at an Earth fixed frame of reference from which we want to see the changes. So a lot of things which might be changing might appear like they're not changing. For example, if you're looking at a geostationary satellite, you see that it's at the same location all the time, but it really is not, right? From a truly spatial sense, it's also moving along with the Earth, rotating, revolving, and whatever the motions which are required, that is being done, and corrections are being made for various other things that might happen over a period of time, right? So now you see that the particular change is dependent on where we are seeing it from. Because we are seeing it from Earth, we are thinking that it is not changing, but if we are, or for that matter, if you are on that geostationary satellite itself, again, we would think that it is not changing. But if you're looking at it from the moon or something else, then you will see that the change is actually happening, right? So this is the important thing to always remember, that there is a level of subjectivity involved, and how we are overcoming that subjectivity is by introducing this concept of frame of reference, and always ensuring that we specify that frame of reference so that there's no room for confusion in terms of how this is calculated. Okay, so let me just skip that. The simple rotation and simple angular velocity is a concept that is very, very useful even in very advanced dynamics, because very luckily pretty much every rotation can eventually be thought of as a simple rotation, because remember that if I have one particular entity over here at a particular angle, and there's another something which is over here, and both of these cases I'm introducing an XYZ system along the length, width and thickness of these two. These two are oriented with respect to each other by a particular way, and to arrive at this I might need actually 2 or 3 rotations in order to get to that. But it's always possible to get a resultant magnitude rotation and identify a particular direction of that vector, so that just through one rotation I can arrive at this. In other words, two bodies, however arbitrarily they might be oriented with respect to each other, I can get from one to the other through a single magnitude rotation, as long as I know the appropriate direction about which I should make that rotation. Which is why, even though it might seem that things are complicated, for example, in the case of the aircraft, you might start with, let's say, these two positions. Essentially they are having the same orientation with respect to each other. Okay, now suppose I give the same angle of pitch, yaw and roll to each of them, but I give them in different orders. Okay, so for example, this is, let's say, pitching, yawing and then rolling, and this is doing everything in reverse. Okay, so now if this is pitching, let's say, then it is yawing and then it is rolling. Okay, now this first rolls, then it yaws and then it pitches. Now these two need not come out, though in this particular case the way I am showing, because of the small angles that I use, it looks like almost they are the same, but it need not be. Okay, so in other words, the order of the rotations will matter, but nonetheless, as a function of all of these roll, pitch and yaw, I can always obtain a particular magnitude of the rotation, such that that overall rotation that has happened, I can always do it in a single fashion, which is what is called as the simple rotation. Okay, but identifying that is of course a challenge, but nonetheless it is theoretically possible. So that simple rotation is what we saw as an example in the previous slide, one of the previous slides, where we looked at A3 as the direction of that rotation. Okay, A3 equal to B3, about which your A1, A2 system was rotating about by an angle theta to get to B1, B2 system. So that's essentially like a simple rotation, and every rotation, take my word for it for now, that every rotation can always be expressed as a simple rotation, as long as you're able to identify this guy k hat, which is the direction about which that rotation has to take place. So before we get into rotation itself, which is a little more complicated to deal with, because you have to do it either using Euler angles or Rodriguez parameters, etc. Some singularities are involved, and there are ways to avoid that singularity, etc. We will get to some of those examples when we are ready to do that. We have the tools to be able to understand that. Very interestingly, when we were doing the translational things, we learnt about position first, and then we went to velocity, then we went to acceleration. Here in rotation, it's much easier to deal with angular velocity than it is to deal with the finite rotation, what we call as a finite rotation vector, but it's very much more difficult to define that. And you already got a taste for that, because remember when we introduced the intrinsic coordinate, we said that it's very easy to get your velocity s dot et hat, right? But to get to the position vector by integrating that is a challenge. Okay, so similarly in the case of the rotation, you have much more, you can much more easily define velocity, namely the angular velocity, rather than the angular orientation or the specific particular attitude of the aircraft at an instant of time, or how it is changing with respect to time. Okay, the rate at which it is changing with respect to time is angular velocity, and that can be determined much more easily, and that of course is a vector, and like any velocity, angular velocity is also a vector. Whether it in fact it's not a right statement to say even in 2D or 1D it is still a vector, just that it was too trivial to mention the unit vectors associated there, but in 3D you have to do that, right? Now consider two frames of reference, because whenever you want rotation, you want to look at the relative motion from one to the other, and therefore you need at least two frames. So in this case, let's say an aircraft fixed frame and an inertial frame of reference A and I. which you see over here, corresponding unit vectors for the aircraft frame are A1 hat, A2 hat, and A3 hat coming out of the screen. Similarly, you have an IJK system which is associated with the inertial frame of reference. For all practical purposes, I can be E, which is the Earth fixed frame, but if it's not sufficient, you have to go to S, which is a sun fixed frame, or to Z, which is a zodiac fixed frame, but most situations will not require that, especially for aircraft dynamics. Now, whereas you might for spacecraft dynamics, depending upon the interplanetary nature of the missions. Now, if A rotates with respect to I, as it has in this particular case, by an angle theta that you see over here, and it's about a fixed axis, which in this case is k hat equal to A3 hat, the same simple rotation that we dealt with in terms of the A and B system. Now we are dealing with the A system and the IJK system. Okay, so you can think of both happening simultaneously. Like for example, that B that we talked about could be a flap in the aircraft. So now that flap deflection with respect to the aircraft is what we looked at over there. Now the aircraft itself is rotating with respect to the Earth or inertial frame of reference. So now you can actually combine, and when you deal with simple rotations, that's a huge advantage, that you can go from one system to another through intermediate systems, and therefore just add them up eventually to get to your total rotation of with respect to the Earth of that flap. Okay, in between, of course, the aircraft coming up. Now, the aircraft rotates with respect to the inertial frame of reference about the axis which is fixed in both the frames of reference, which is in this case K or A3, and therefore we call it simple rotation. That's the term simple rotation, is that you should have identified that vector about which the rotation is taking place. As long as you have not identified that, it seems that it's not a simple rotation. But every problem can be reduced to a simple rotation once you identify that. Okay. Now, so say about k equal to A3, hatted both of them, of rotation amount or magnitude, which is theta, which is of course a function of time. So this is at a particular instant in time. At some other instant, the angle could be changing. It need not always be monotonously increasing. It could be increasing, decreasing, or making a vibratory motion, which is essentially going either way. Suppose you want to induce a particular kind of a motion like a phugoid, etc., you might do something like that. Now the angular velocity vector omega, again there's a notation that we use very similar to velocity vector or the other things that we have been talking about. So for example, now we are talking of the angular velocity of the aircraft with respect to an earth or inertial frame of reference, which is what we write in this way, A/I. Another way of writing it is to put A over here as a superscript and put the I on the top over here. Same what we did with velocity, we are doing with the angular velocity, because it's also another kind of velocity in angular motion. Okay, so now because we have been able to identify k hat, therefore we can put it as magnitude of that rotation, how it changes with respect to time, that is the theta dot. And theta dot, remember, you don't need to specify the frame with respect to which you are taking the derivative, because theta is a scalar quantity, it's a scalar measure number of what is the angular motion over there. But the identification of k hat is the challenge over here, because only then you can put it in this simple form that omega is equal to theta dot times k hat. In fact, many of the problems that you did today in the morning, you are looking at angular velocity and just using this theta dot. It's just angular speed, remember. It's only when it combines with k hat, it's the angular velocity. Otherwise, you cannot really call it an angular velocity as such. Okay, theta dot by itself is an angular speed, though many books even mistakenly call that itself as angular velocity. It's this combination which is the angular velocity. So this simple angular velocity of A in I for a rotation theta about a fixed axis k hat, which is, remember, fixed not in just one frame of reference but in both the frames of reference. We are talking about a rotation and an angular velocity of one frame with respect to other, namely the two frames involved are A and I, and with respect to both of them this k hat is fixed, because in one of them it's called A3 hat, the other it's k hat, but both of them are identically equal to each other for whatever value of theta that you have at whichever instant of time always this is holding good, which means that that is a fixed axis about which the rotation is taking place, right? Now this is valid for simple 2D rigid body dynamics cases from chapter 3 as well as chapter 4, where it is very easy to identify your k hat. But when we go to 3D, it becomes a little difficult to identify your k hat, even though theoretically it is possible, and there we have to look at alternate ways of doing the same thing, right? So we may refer the scalar quantity omega equal to theta dot, as I already said, as angular speed, but not angular velocity. That's important for you to remember. Okay, now coming to omega, it's relating the differentiation in two frames of reference. So in other words, angular velocity, the concept that we introduced, is not only useful for understanding the motion of a body with respect to a frame of reference, like what we said of a flap with respect to an aircraft, or an aircraft with respect to the earth, or the flap directly with respect to the earth through the aircraft, right? So in addition, this tool, this quantity or this particular entity that we have introduced, omega vector, can also be used for other things which were usually very difficult for us to carry out. Now we can carry out in a much easier fashion. Okay, so this is the first thing that we will use it to showcase the power of omega, is that it can replace a derivative through a cross product. So you don't need to use calculus, you can use linear algebra. If you thought linear algebra was simpler compared to calculus, then this will, differential calculus, then this will be very useful for you, that you do not need to do a differentiation. You can just take a cross product and end up with a differentiation because of that cross product. Okay, let's see how that happens. Now let's take any vector, arbitrary vector q. It could have any dimension, it could have any magnitude, any direction, and any two frames of reference, which we will call as, let's say, I and A. It could be the inertial and aircraft fixed frame, for all you know. And now there's an important relation that we will in fact utilize throughout this course towards the in fact pretty much every one of your homeworks will actually require this. So it helps us simplify derivatives. See, taking the derivative of q with respect to time, the complexity will depend on which frame with respect to which you are taking the derivative. Many a times taking the derivative of the vector with respect to an inertial frame will be very difficult, whereas it will be much easier to take it with respect to the aircraft. Going back to our simple problem of the, let's say, the flap rotation, you would see that you know how it is changing its orientation with respect to the aircraft, but you don't know how it is changing with respect to the earth. So there is a transition that is taking place. Now it need not be rotation vector, because this q is any arbitrary vector. It could be a velocity, it could be an acceleration, it could be a position vector, or any other vector that you would like to have. It could be from, let's say, an electromagnetic field, doesn't matter. As long as you know its derivative in one frame where it is very easy to take the derivative, or it is quite obvious, then you can get it in any other frame, as long as you knew the angular velocity of the frame in which you know the derivative with respect to the frame in which you do not know the derivative. Okay, so to get from a known frame to an unknown frame, all that you have to do is to add a term which is not having any derivatives, but is just having a cross product, and that cross product involves the angular velocity of one frame with respect to the other, and is that same vector on which it is whose derivative you would like to determine. So in other words, this operator I d by dt is now being defined as the same derivative with respect to another frame A, and then you have an omega of A in I crossed with that quantity. Okay, so this is the kind of operator system that we have, that taking a dot in any arbitrary frame can be done by just adding a term which is a cross product of that. No derivatives are required. But this typically in per particular frame, it might be very easy to calculate this derivative, or it might even be known intuitively, and therefore all that you need to do is just to add this term and you end up with the derivative. So this is a very important result that we will continue to use time and again. So this could be any arbitrary vector, so which we have denoted by q over there, and it could be of any dimension, doesn't matter. As I said, it need not be in mechanics, it could be in an electromagnetic field related vector, doesn't matter. All of the vectors can actually be transformed in this particular way. Yeah.
So, and this only works for the taking derivative with respect to time?
No, not necessary. Yeah. See, because your angular velocity with respect to time, right? So it's a very, very good question that you asked, because there is something like, for example, this is if you want to calculate the derivative with respect to s, then you could use instead here the curvature vector. Okay, so you will have something or the other coming up here. You will not, if it is angular velocity here, then what you said is absolutely right, that it has to be a time derivative. But if it is something else, then you can always discover a particular vector, or you can multiply these by like what we did, for example, ds by ds, and then take ds by dt as s dot and make it dq by ds, right? So then you have to do that for the this term as well. But essentially, so that's good that you pointed that out, that it's always involving a time derivative here, because angular velocity by definition is change of angle with respect to time, and it's the change in orientation that we are interested in over here, that going from one frame to another frame, and therefore that's important. Good. Yeah. Angular velocity is the key to differentiation of vectors in rotating frames of reference. Like for in this case, your aircraft can be rotating, as we said, pitching, yawing and rolling, and anything which is moving on that to get to its angular velocity from the angular velocities of those control surfaces, for example, becomes much simpler. So in addition to providing, of course, the original reason why we introduced the angular velocity is to provide info about the rigid body's angular motion, but it's serving additional purposes, and this is one such purpose. So if the vector is fixed or unchanging in A, so that particular q that we talked about was any arbitrary vector to start with. But now we take a special case. Let's say if it is fixed in A. So if it's fixed in A, obvious that the d by dt of that vector in A should be 0, because that's what being fixed means. It doesn't change with time, right? So therefore your first term will vanish, and therefore you will see that the differential operator just becomes a cross product operator over here. Okay, this is the simplest form in which that can be utilized. There are other cases also when one of the terms can drop off. For example, your second term can drop off under multiple situations. One is the very trivial case where q is 0. You're talking of the of a null vector whose differentiation, irrespective of which frame it is taken in, will always be 0. Doesn't matter. So therefore this term will vanish because q is 0. The other is if a and I are changing in time, having a motion, but they are changing in such a way that they are always aligned in the same way with respect to each other. So essentially your angular velocity of A with respect to I is 0. So in that case also any arbitrary vector differentiation either with respect to I or A will remain the same. It's only if the orientations of two bodies or two frames are changing with respect to each other, then that vector's derivative will depend upon which frame with respect to which it is taken, and that difference will come through this. So one case we already saw in this particular example, the first term vanishing. Now we have seen two examples of this second term vanishing, where either q equal to 0, very trivial case, or if A and I are not rotating with respect to each other, in which case omega is 0. What could be a third example in which case the third term will drop off? We have seen an example where this drops off, or this drops off, or this drops off, making it simpler, right? So can you think of another example where this becomes simpler?
If those two vectors are parallel.
Very good, yeah. So essentially these two vectors that you're seeing over here, if they happen to be parallel to each other, then obviously this is going to be 0. What does that practically mean, Daniel? omega and q being
They're in the same direction. So it'd be
Yeah.
like if you had, I guess, a velocity that was going upwards and you were rotating about that axis, it
Right,
wouldn't matter what
right,
frame of
right,
reference.
right. So remember that your q is any arbitrary vector. So as long as you're aligned that arbitrary vector along the axis of rotation. So if that vector is always along the axis of rotation, then obviously you do not have this term, and therefore it's immaterial with respect to which frame, which of those two frames you are going to take their derivative. Good point. So that's this. Then now let's take a step back and look at velocities. We're looking at angular velocities. Now we want to go look at translational velocities. Of course, we have understood translational velocities from a different perspective earlier. Now that we have introduced angular velocity, there are easier ways of calculating the velocity vector and even the acceleration vector, which is what we will try to introduce now. So in order to understand velocity, of course, it is with respect to a frame. So we introduce the frame, which is the inertial frame of reference, and on that we fix a particular point, which is the origin, which we call as O. So, and that's a point which is fixed on the frame of reference. So the position vector is drawn from O to a particular point P, and we have to see how that changes with time in this particular frame of reference in order to get to the velocity vector. Now, this part of the story we already know. What we do not know as yet is how to take advantage of the angular velocity that we have introduced in the previous slide, which is what we will try to do over here. So we have this point P, which is moving in I, this inertial frame of reference. Now, how is the velocity of P in I defined, which we already know, is that it is the d by dt of the position vector. And that position vector, you can either call it P or R, doesn't matter, but it's going from that fixed point O, fixed point I mean fixed in I, that point O, to the point whose velocity we are interested in, namely P, or that particle at that particular location, right? Now, the simpler notation for d by dt is the dot that we have been using, and because it's just one frame of reference that we are talking about here, we can think of that as the default and drop off the pre-superscript I, and therefore just call it as an r dot of the r dot, and that r of course is from O to P. Okay, now that we understand the very basic definition of velocity, we understand the basic definition of angular velocity, now we can combine it for various problems which keep recurring in dynamics in various situations, various forms. They might look very different from each other, but they have a lot of commonality in them. One such thing is 2 points which are fixed on a moving rigid body. So in other words, the moving rigid body could be an aircraft, and there are 2 points. Let us say we fix one point at the nose, let's say one point at the starboard wingtip. Okay. Now, with respect to these 2 points, suppose I'm able to track the nose of the aircraft. Using that, can I get the motion of the tip of the starboard? Okay, that's something that we can try to do using these 2 concepts that we have introduced, namely the velocity of this is known. Now we want to get to the velocity of this point, but I want to do that using the angular velocity of this particular aircraft, so that things are much simpler. I don't need to get to it, the velocity of this point, from the scratch, from the fundamentals, from the definition that I showed on the last slide, which is much more difficult to calculate. Now that, because I know the velocity of another point on the same body, why not utilize that and the angular motion of that body in order to calculate velocity of any other point on that. Though I talked of an example of a nose point and a starboard point, more often this will be used as the center of mass. You would know the motion, and using that you will get to the motion of any other point on the aircraft that you're interested in. Okay, so it's a moving rigid body, it could be an aircraft. So relating the velocities, of course, both are inertial velocities we are talking about. In other words, velocity with respect to the frame I of 2 points, we'll call those 2 points as P and Q. Okay, now these are fixed on or in a rigid body A. Why on or in? Because it could be on the surface, it could be inside the aircraft, it could need not even be a material point, because For example, it could be some location. In fact, the center of mass of the aircraft could be somewhere in between in the cabin where there's no material. Okay, it could be just air, pressurized air inside the cabin. So it doesn't matter. You're essentially talking about something that is fixed on or in this rigid body A, or it could be even entirely outside the aircraft. Okay, so it doesn't matter as long as it is fixed with respect to the aircraft A, both these points P as well as Q, and if I know the velocity of one, I should be able to get to the velocity of the other. Similarly, if I know the acceleration of one, I should be able to get to the acceleration of the other. So that's the purpose of this slide. So the velocity first. So velocity of the point Q is known, let us say. This could be, for example, the center of mass that I'm already tracking somehow, and then I want to get to the velocity of a particular point on the aircraft, let's say on the horizontal tail or on the rudder, etc. I want to get to that. How do I go about doing that? I need to have the angular velocity of A in I, and then I have to just take a cross product of the position vector between these 2 points, starting from the point that I have information for and going to the point that I'm interested in getting the information for, which I don't yet have, right? So going from Q to P, that is what is the position vector. And this, you see, is having a form very similar to the general thing that we talked about for any arbitrary vector Q. If you want to take the derivative in one frame with respect to the other, how do you go about getting that? Just adding a cross product of the angular velocity, because remember that this velocity by definition is the derivative of the position vector, and that position vector is what we are talking about over here. So therefore, this is the derivative of R from O to P, and this is the derivative from O to Q, right? But P to Q, is both are fixed on the rigid body, and therefore there's no relative motion between them. Okay, which is why you would see that if you can write OP as OQ plus QP, and then you can get to using the fact that one of them is a constant and therefore it doesn't change, and therefore only one of them changes, and therefore the difference between the velocity of these 2 points, let's say the center of mass and any other point on the aircraft, is this particular term, which is the cross product of the angular velocity times the position vector from the known point to the unknown point. Once again, these 2 velocities will be identical to each other under those 3 conditions that we mentioned. Either the aircraft is not having any angular motion, or we are looking at the trivial case of both the points coinciding at maybe at a given instant of time. Okay, they could be at a particular instant of time they are same, but of course remember we're talking of it both being fixed on the rigid body, so it has to be for all times if it is at a particular instant of time. Or as Dan pointed out, if these 2 are parallel to each other, in other words, for example, let's say the center of mass and the nose tip. Okay, I know let's say the center of mass velocity, which is Q, and I do not know the nose velocity, which is Vp. If I want to determine that, they could be the same, identical, if, for example, the rotation that is happening is about the line which is joining those 2. Maybe the center of mass to the nose is about which the roll is happening. So even if it is rolling, you could still have both those velocities the same. Okay, so that's the kind of example that you came up with, and those are trivial cases, but even in the general case where none of these things are non-zero, that's where the power of this particular equation will become evident for us. So the whole idea is knowing the velocity of just one point on the rigid body, that's enough for us. And of course we should know the body's angular velocity. Okay, once we know these 2 guys, then for any other point, because we can say how that point is related to Q by through this RQP, and therefore we can go ahead and use this equation to find out the velocity of any other point. Okay, so this is very, very useful for us, because otherwise calculating the velocity from the first principles, from the derivative of the position vector, each time from O, that inertial frame of reference, is very, very challenging and difficult, and it's unnecessary drudgery to do it over and over again. As long as you've done it for one point, let's say the center of mass, you can do it for any other point. Okay, even though for the sake of example, I'm every now and then calling Q as the center of mass, Q need not be the center of mass. It could be any point, any arbitrary point which is fixed on the aircraft, just like P is. Okay, now one can find the velocity of any other point on it. Okay, now that we have dealt with the correlation between velocity and angular velocity, now we want to correlate acceleration, which is your translational acceleration that you're already familiar with angular acceleration. So those of you who would like to understand this a little more deeper with examples, etc., you can always go to this particular section, though what I am covering is not from the book, but just for you to see the parallels of what we are doing over there, right? Now coming to the angular acceleration, see in the previous case also, when we were trying to relate the velocity and the angular velocity, we had to first of all introduce the concept of angular velocity because we were not aware of it in a generic sense. Okay, we knew about angular speeds, we were using it also in our calculations, but we didn't know it in a general form, in a three-dimensional form as a vector. Similarly, as of now, I'll assume that none of us know about angular acceleration. So we will first introduce the concept of angular acceleration and then correlate it with the translational acceleration. That will be our learning path. So the angular acceleration again obviously involves rotation between two bodies, and that rotation changing in a complicated way with time, and that means that you need at least two bodies to deal with. They could be either actual rigid bodies or they could be frames of reference, or combination. One could be a rigid body, one could be a frame of reference, doesn't matter. For all kinematic purposes, these two can be used interchangeably. I can either call a frame of reference as a rigid body or a rigid body as a frame of reference, really doesn't matter. But when I go to kinetics, I have to be a little more careful because then the rigid body's mass properties, especially the inertia properties, etc., will make a huge difference. Therefore, these two are not one and the same. Okay, but for all kinematic purposes, they are one and the same. So again, we are using the same two notations, a frame I and a frame A. Again, just for visualizing, I'm calling it an inertial frame of reference and an aircraft, but it need not be. Okay, I could be any frame, need not be inertial also. Okay, inertial frame requirement, as I said, is only in kinetics when you want to employ Newton's second law, not now, right? But just to get ourselves ready for it, and since this is for any two arbitrary frames of reference, I'm just calling it an inertial frame of reference, need not be. Okay. Similarly, aircraft frame, it need not be fixed to the aircraft, could be any arbitrary frame, inertial or non-inertial. Now the angular acceleration of one frame with respect to the other, A with respect to I, is defined, is given the notation alpha, and of course the more precise notation will be of A in I, and again you have to specify a particular frame of reference, which if not specified is essentially the frame with respect to which you are taking. So essentially in this case it is specified. So there are two ways of writing this as before. You can put it as subscript A/I like what it is written over here, or you can put this A as a superscript and put I as a pre-superscript so that it is I alpha A. Both are acceptable and commonly used in different literature. Okay, so now coming to the definition. We already have introduced omega, we know what it means. The time derivative of that omega with respect to I is what we are calling as alpha. Straightforward, right? Just like how we went from translational velocity to translational acceleration, we are going from angular velocity to angular acceleration, omega to alpha, just like we did from V to A. Now, a short form notation for that would just be a dot, like all time derivatives are for us, and when it is not specified with respect to which frame, the default is the inertial frame that we are talking about over there. Now this is valid again, like all the previous slides that we've been doing this afternoon. It doesn't matter whether it's 1D motion, 2D motion, 3D motion, etc. Any dimensional motion for that matter, this is going to be valid. Okay, just that it will become too trivial in some of the cases. Now for simple rotation and simple angular velocity, that is you can think of it as 2D. But essentially, as I said, any complex motion also can be reduced to this as long as you know the vector about which the rotation is taking place, namely k hat. So in that case, we know already from the previous slides that your angular velocity vector is given by its magnitude times its direction, which is along the axis of rotation. Now, if that is the case, then it's very easy to say, because k hat is not changing with time, because that's the simple rotation that we are talking about, that it doesn't change with respect to time, and therefore the time derivative of this comes out, and just this alone you need to take the time derivative. Therefore theta dot becomes theta double dot. Okay, so that's the magnitude of the acceleration, angular acceleration, and this is the direction of the angular acceleration, which is coincident with the direction of the angular velocity. Both angular velocity and angular acceleration are along the axis of rotation. Okay, now that we have looked at angular acceleration, it's very interesting that we need the concept of angular velocity to be able to calculate velocity, translational velocity, much easier. We always think that translation is an easier thing to do, but introducing angular velocity first helps us to calculate translational velocity in a much easier fashion. Same thing with acceleration. Knowing about angular acceleration, even though it seems to be a relatively more complex topic, helps us to evaluate translational accelerations much easier manner. Okay, now we consider a point P which is moving in the frame of reference I, and we already have defined the velocity of P in I as the time derivative of the position vector from the point fixed in the inertial frame O to that particular point whose velocity we are interested in, namely P. So R from O to P, we take the derivative with respect to frame I. Okay, which again we have other notations for it, as instead of putting a d by dt we put a dot, and we drop the I pre-superscript because that's the default value, and we just call it as R dot. But of course it has to be made amply clear that that is the default value, because without frame of reference actually has no meaning, very ambiguous. Where O of course is any point fixed in the frame A, or which is actually I think it should be I. Okay, it should be I. Okay, now define the acceleration of P in I is to take one more derivative, right? So because the time derivative of the velocity is the acceleration. Now this is the way we have known acceleration so far. In the next slide we will take advantage of the angular acceleration that we just introduced. Okay, so this is, as we know, that acceleration is the time derivative of the velocity of that same point whose acceleration you are interested in. So here also it's P, here also it's P, and it is with respect to the same inertial frame of reference I. When we do that, we can again use the simplified notations of a dot instead of d by dt, and dropping off the I as well, or bringing Vp as ROP dot, and therefore it becomes a double dot, which is the second derivative of the position vector from O to P, where O is fixed in inertial frame and P is the point whose motion we are trying to tackle. Now let's say we have that same problem that we already discussed, that there are 2 points which are fixed on the moving body on an aircraft. Let's say the nose or the starboard point or the center of mass, any one of those, or any other arbitrary point on the aircraft. Both are fixed with respect to the aircraft, and we could relate earlier those two velocities. Now we want to correlate their accelerations, which is a little more complicated, but doing it this way is definitely going to save you a lot of time and effort compared to doing it from first principles like what we did in the last slide. So again, we introduce the same 2 points P and Q. Again, they are fixed on the body or in the body or with respect to the body, the rigid body A that we are talking about. The velocities and accelerations in I are related. So already we have shown how the velocities are related. If you know the velocity of the point Q, you can get to the velocity of point P, both in the same inertial frame of reference. How you do that is just by adding a cross product, no differentiation required. The cross product is of the angular velocity of one rigid body with respect to the inertial frame, and then you have to cross it with the position vector from the known point to the unknown point. Now can we do the same thing with respect to the acceleration? Yes, we can. So it has a similar structure, just that you have to add two terms now, not just one. And that once again, here Vp is equal to Vq plus something. Here also AP is equal to AQ plus something. So in other words, we know the acceleration of this point Q, but we do not know the acceleration of P. So Q, for example, could be the center of mass of the aircraft, and P could be any arbitrary point on the aircraft, both being fixed on the aircraft. And therefore, we have to add two terms. Once again, both these terms require no derivatives. It's only cross products, okay? One of them requires just a cross product like the previous one. Here did angular velocity times the position vector, a cross product. Here it's angular acceleration times crossed with the position vector. But what new thing that we have over here is an omega cross RQP, and that you can easily see. All that you have to do is to go to the definition of the velocity that we did in the previous slide, apply that both to Vp and to Vq, and then you get it in terms of the accelerations and the angular accelerations, because d omega by dt is alpha, so that's how this alpha crops in. And again, when you're taking the product, you have to go u dv plus v du. That u dv derivative of this is resulted in this, derivative of this has resulted in this. So you have two terms that are coming out of that, right? So you have three terms, whereas you had only two terms over here. The first term Vq became AQ after the time derivative, whereas this you have to take it as u dv plus v du. Therefore, there are two terms. One is quite obvious. When you're taking the angular velocity, time derivative becomes angular acceleration. When you're taking the time derivative of this and expanding it out, you get this particular thing, because remember that we are using the other formula that we derived, where the time derivative of a vector can be written as the time derivative plus a cross product, and that time derivative is 0 because our QP doesn't change with time, because both points Q and P are fixed on the body, and with respect to that body we are taking the time derivative. So therefore you will see that this is what happens. But now let's pause a bit and look at something very similar to what we had looked at earlier, because we are looking at two omegas which are multiplying each other. Of course it's a cross product, but essentially you can think of it in your mind as, in terms of the magnitudes, an omega squared being involved over here, okay? So that omega squared times r is something that you're familiar with. You had earlier seen it, right? What was that? Yeah, centripetal acceleration, and we are dealing with accelerations now, so it's obvious that that has to come through, right? So that centripetal acceleration is coming in. How is it different from the centrifugal acceleration? Yeah. Yeah. So, but in terms of signs,
It's positive.
yeah, which is positive?
Well, I think it's centripetal being negative.
Yeah, because centripetal is seeking the center. That's what it means. Means moving towards the center, and our positive direction for the radial coordinate is away from the center, right? So which means negative. But why are we getting a positive here then? Yeah.
So how to do that is the cross product twice.
Yeah, yeah. So it's along those lines, but you need to actually explain it a little more. But that's how the negative sign comes up. So the negative sign is contained in the fact that you're taking two cross products over there. Okay, so you can just try to check that out. If you're unclear about it, we can discuss that in the next class. The other thing that I want to talk about is, you know that, for example, just a few slides back, Daniel said that one way in which r cross omega cross r can go to 0 if both of them are parallel to each other, right? So any cross product will go to 0 if they are parallel to each other. But now we have omega and omega, which are Omega is parallel to omega, obviously it's the same vector, right? So why isn't this going to 0?
Because you cross it with RQP first.
Come again?
You cross it with RQP.
Exactly. So this bracket is the reason for that. So this has to be done first, which means that this vector that you get after crossing this will be perpendicular to both of these and therefore perpendicular to omega. Okay. So therefore, omega with a vector which is perpendicular to omega is going to give you a non-zero result. So that's why this is a very important bracket to remember. Okay. If you forget that, then that term can actually drop off. So yeah, so that is contained. So again, the other thing that we have, remember that this is a general expression for the acceleration and therefore should include not only your centripetal but also your Coriolis. Where is that?
Alpha cross.
This one? Yeah. How is the alpha containing that?
Alpha is angular acceleration.
Hmm.
So it is derivative of velocity.
Very good. Yeah. So just like this centripetal, remember, is a radial direction thing. The Coriolis is an angular thing, which is essentially along E theta hat, and that has to come through your alpha because alpha is rotational acceleration that you're talking about, angular acceleration, and therefore it is contained within that. Okay. This is not entirely that, but it's contained within that. So knowing acceleration of one point on the rigid, yeah.
So would you say the centripetal and Coriolis accelerations are like the radial and tangent accelerations? Would you say that?
Yeah, yeah. So it's not the entire thing. Remember that yeah. So along with this ER term, and you have the E theta term, right? These were the obvious ones. Along the R direction, you should have an R double dot. Along the theta direction, you should have a theta double dot. And because it's not length dimension, you are multiplying with R. So that's essentially what is coming out. Okay. So I'm making it seem as if we are making this up, but we know, you know, that we have derived these things. Okay. So now this is not all, right? So you have, along with R double dot, you have one more term, and here also you have one more term, right? So that term here, of course, is negative. So negative. And what is that? That is your centripetal acceleration that you had, right? So what is the expression for that? You remember that?
R theta dot.
Yeah. You wrote it quite a few times on the for your homework, right? So next, what about this? The Coriolis.
It's 2R dot theta dot.
Very good. Okay. So this is what I was telling Lalita. You asked whether one is radial or the other is tangential. You can see that this is the expression that we got in the polar coordinates, right, for the acceleration. So this is the polar coordinate acceleration. That is equal to this, and you see that the centripetal is coming as part of the radial direction and the Coriolis is coming as part of the tangential direction. Yeah. Okay, so knowing the acceleration of one point on the rigid body, namely let's say Q, we can get to the acceleration of any other point, any arbitrary point, namely in this case we're calling it P. But if we know, of course, a few things. One is the acceleration of the first point. We want to get acceleration of another point. We need the angular velocity of the body itself on which both of these are fixed, and we need the angular acceleration of the body in which both of these points P and Q are fixed. Okay, so once we have omega and alpha, the only other thing, of course, is we know these 2 points. Therefore, the position vector from one of the points whose information we have to the point whose information we do not have are from Q to P is all that we require, and only cross products. We just have to take those cross products and add it to the acceleration of the point whose motion we know. We will get the acceleration of the point whose motion we do not know. But the requirement is that both those points are fixed. Okay, so that's an important requirement. Don't end up using this for 2 points where one of the points might be moving with respect to the other point. Like for example, I cannot use it to understand the flap deflection or a rudder or any of the control surface deflections, okay? Because one point is moving with respect to the other. But I will still be able to use it maybe to the hinge of that control system, and then from the hinge I know the motion of the control surface, and therefore I will be able to go in steps, and therefore you might be able to use this as part of the solution process, not the entire solution process. Okay, so far clear everything? Yeah, we'll go ahead. Oh, okay, I think we are run out of time, so maybe we'll do this the next class. We are past 4, so we'll do something very similar in the next class, where we'll talk about the same 2 points fixed on the moving rigid body and utilize that in order to understand a few other things, like the more complex thing of the control surface motion as we go forward. Thank you.